this afternoon. So, as the title of this paper is exploring a modular architecture for sensor validation in digital twins. And yeah, so basically this work is related to Signify, and it's a project funded by the Research Council of Norway that has funded NTNU and CTEC. It is also a research institution in Norway. So with this, and what I will present is a little bit part of the little work that is part of this project. This project students and one postdoc. And today I will discuss a little bit of some of the work that is included in this project. So just to give you an idea, this whole project is based with the sensor validation in digital twins. And of course, the idea is not to focus on developing the whole digital twin. That is a very huge task, and focusing on a specific aspect that is relevant for digital twin. And we have different work packages and different people working to different approach for this sensor validation. Some students are working on more model-based approach to sensor validation. Some, this work that I will present today is the part that is related to machine learning and data-driven sensor validation. And some of them are digital twin. What is digital twin? I don't know, maybe most of you are already familiar. You know that there is not really a unique definition, a real definition of digital twin. But what I usually like to think is that a digital twin, like first thing is that let's assume that we are a sort of collection of simulator software for a specific physical asset of interest. Physical asset can be an industrial plant, can be a vehicle, a ship, or can be a human being. We can think about digital twins of very different things, right? And then let's assume that we have a set of simulators that are capable to simulate the behavior of small components, subsystems, bigger part of the system and the whole system, and they can act in a coordinated way, really mimicking what is the real behavior of this physical asset. Then also, let's imagine that you have sensor on the physical asset coupled with an IoT network, such that you can real-time measure information on the physical asset, and with this IoT network, you can inject this real-time information from the physical world into the simulators. What this means is now enabling you to run simulations that are starting initialized with real values from the real world. Then at this software, let's again imagine that you have AI capabilities, what-if analysis. You can start running what-if analysis on this physical asset based on real data that are in real condition, in real time. So you load the data of your physical asset or your ship or your industrial plants with real data. You run in the simulation what-if analysis, what will happen if I do this or this other decision or other things, and then you can start selecting what is the best way to operate. Then you close the loop by sending, based on this what-if analysis, actions on the physical twin, and then again, your sensor network can again gather data and monitor real time if what is happening in the real world is what you were predicting or not, and starting saying, okay, something is deviating from expected. You can have this loop really making you a lot of possibilities. The problem that we might have with this thinking is that loading data and making of this physical, this what-if analysis relies on the fact that data that you are injecting in your digital are reliable. But we know that this is not always true. Sensors may be failing because they can be unreliable, or it's the communication part of the IoT network that can be failing. So the data that you are injecting in your digital twin might be not really reliable. Now think about, for instance, one of the typical interesting things that you might want to use this digital twin concept is for anomaly detection of some problems in an industrial plant. You want to measure, for instance, you want to detect if there is something going wrong in a pipeline or in a specific part of the device. Of course, your data will measure something anomalous, then your simulation will see that something is not working, then you want to stop and make some maintenance or other things. However, if the data that you are injecting are corrupted by different reasons because of the measurement is wrong or because the communication part is wrong, it might be the case in which in the physical process there is nothing wrong, but your analysis detecting an anomaly just because your acquisition part is creating error. Then you are taking countermeasures that really don't match what you are happening in the physical asset, and still you will have a critical loop that can lead into catastrophic consequences, especially if you are focusing on safety critical systems. So trusting the data that you are loading in the digital twin is quite a crucial part. This is what I'm calling here sensor validation, or if you want, sensor fault detection, isolation, and accommodation, because this is what we are trying to develop. Somehow building a preliminary filter before injecting data in the digital twin. Can we trust those data? And meaning, can we detect if there is something wrong? And in case there is something wrong, can we only isolate which sensor is creating a problem? So which sensor is not really reliable because of the measurement wrong or because communication parts wrong? And then once we have isolated, can we replace those fake measurement with some measurement that is more reliable so that we can keep operating? So this is the framework that we are focusing on. And we are, as I was mentioning before, we are having different kind of approach to this kind of problem. Some are model-based, not presented today, but just to give you an idea, the PhD student that is working on model-based approach is using a framework based on distributed common feature. And data-driven solution is something that I will discuss today. So basically what we have been developing is a modular architecture in which there are the data that are collected for physical twin are processed in 3 layers, in which there is a first part that is a bank of virtual sensors that I will explain later. Then there is a second part that is somehow computing this residual or this difference between what we are expecting and what is the real measurement. And then a final part that is acting as a classifier to identify if there is a problem and where the problem is coming from. This is a more detailed view of this architecture that we have been presenting, in which is first of all, yes. Another clarification, the input that we are considering, we have been splitting in 2 types of groups. One that we are calling the unreliable sensors, and one the reliable sensors. This was coming usually because in some cases, in relevant industrial setups, you might have the situation in which some sensors, some measurements are so important that you have a lot of physical redundancy, or you have some other checks at higher layer because those measurements are so critical that you cannot really admit that something goes wrong with that measurement. So in this case, having this framework which splits the sensors that we have available in 2 groups, some that are reliable, that they are meaning you can trust what they're measuring, and some that are more normal sensors, which again, as I was saying, the measurement of the communication part is not wrong, is just to be more general. Of course, if you have a system, if you're considering to apply this to a system setup in which you cannot really trust 100% any sensor, then this group will just be empty. But in some cases, it might be useful to consider this because this is what you will find in practice. Then these sensors are then entering a group of virtual sensors in which, based on the measurement, what we are doing is trying to predict each one of the sensor measurement based on the remaining measurement. So for instance, the virtual sensor number 1 is trying to predict sensor 1 measurement, having as input all the rest of sensors except number 1. This sensor number 2 will be the same, excluding sensor number 2, and so on. So it will be the sort of cross network in which each measurement is relying on the rest. So the idea is to create a sort of cross-dependence network to see how sensors are related to each other. Because typically in a physical aspect, you will have, I don't know, in an industrial plant where you will be measuring temperature, pressure, flow, and other things. These things are related to some physical phenomena that introduce correlation or other more complex linear dependence. So it's quite common that somehow information from one sensor can bring information also on other type of measurements. And then investigating on the capability of some measurements to predict other type of measurement is a way to understand if the process is acting as expected or is deviating and there is some sort of anomaly. For instance, one underlying assumption in this approach is that if there is a physical anomaly, like a leakage or other physical process, this most likely will change and create some unexpected behavior, not in one sensor, more in a group of sensors. While if there is an anomaly in a measurement or in the communication part, most likely this will be isolated. So all the rest of the measurement maybe will keep as expected, while only one individual measurement will deviate from the normal behavior. So this is a situation completely different from a physical anomaly, and this is why we think that with this kind of cross analysis, we can differentiate, because remember, we want to focus with this work, we want to focus on this kind of sensor faults, not on physical faults in the real process. Then once we have computed this kind of estimation of this virtual measurement based on the remaining set, we compute the difference between the expected value based on the remaining measurements with the actual value that has been measured, and then collecting all these type of residuals in pairs, we give this set of residuals to a classifier that based on these residuals is trained to identify patterns that points to there is something wrong or not. And in case there is something wrong, which one of the sensors is more likely to have created this unexpected pattern. And of course, you might imagine that a nonlinear classifier is needed because typically an industrial plant or some other physical asset will be involving nonlinear relations among the measurements. So it's not quite intuitive based on looking at the residual, which one is creating the problem. Because of course, it's not necessarily true that the residual that is deviating the most is associated to the sensor that was introduced in the fault, because of this complex nonlinear behavior that you might have in the physical asset. So the woodwork was actually published in the sensor journals, our main journal related to the conference in 2021, in which this architecture was developed, presented, and tested on different datasets, public datasets with different class of faults. What we are presenting here is a sort of, so as I will introduce, mostly the original work was developing this architecture with the multi-layer perceptron selected for each one of these layers. In this work presented here in the paper in the sensor conference, what we have been doing is checking different choices in this kind of architecture of different networks to see what kind of impact might have a different network. For instance, we have checked some convolutional layer network or other type of networks, how they impact the overall performance of this architecture. So that's why exploring this modular architecture with different specific solutions at each individual component, that, as you might imagine, might have impact in terms of performance, but also complexity. So the basic idea was that we have this estimation layer in which basically, as I was saying, we process with a sliding window mechanism. We collect actually not just the inputs, just in order to capture both the temporal and spatial dynamics of the measurements. The input, for instance, again, to virtual sensor 1 is not just the current measurement from sensors 2, 3, and so on, but it's also some past measurements from the sensors with the sliding windows that is going from current time to, in this case, t preceding instance. So just in order to exploit also temporal patterns that are present in the physical asset. And what we were proposing at the beginning is a classical multi-layer perceptron network. And this was shown to perform good enough, at least in 2021. So the performances we will see were quite good. For the residual, we were just simply considering a difference between the prediction and the actual measurements. And then again, for the classifier part, we were selecting a simple multi-layer perception with a sigmoid activation at the output. What we are doing now is, well, after that, we have been doing different directions and also changing this architecture. But what is presented in the paper here at Sensor Conference, what you will find is that what happens if instead of considering this multi-layer perceptron for the classifier for the estimation, we have different combination based on multi-layer perceptron, on convolution neural network, on gated recurrent unit, recurrent neural networks, and other types of networks. So, and we have been just checking basically performance and complexity of these different combinations to see how much this kind of modular architecture can change performance and complexity depending on what is the specific module that you are using. And also, this part here, the autoencoder, was at least what we found in 2021 when we were presenting the first part, the first idea, was what we consider state-of-the-art. At least this work based on autoencoders from a group in Linköping University was exhibiting the best performance, at least according to our literature research at the time. So we were already capable to slightly beat this performance based on the autoencoders with the first work with the multi-layer perceptron, but we can see that now with different combinations we can go even better than our original. The journal paper, so with the first proposal, were tested on 3 datasets that are publicly available, one on air quality measurements, one on wireless sensor network measurements, and one on this synchronous motor. While the work of course, for space reason, the work in Sensor Conference, that is only 3 pages, we just selected performance on this dataset. And so the measurements are coming from real measurements. The faults that we are considering to see how we are capable to detect, identify, and accommodate faults are synthetically generated and superimposed on the real measurements. And again, in the original journal paper, we were considering 4 classes of faults: bias, drift, freeze, and noise. In the conference version here, we have, again, for this reason, we only considered bias faults. It's worth also mentioning that we are focusing on weak faults, meaning when the fault is very small with respect to real measurement. The reason for focusing on weak faults is these are typically much more difficult to detect, because of course, a strong fault that they end up with an out of range measurement is very easy, right, to detect, and you don't need a complexity. While weak faults that might be hidden, that are still within the range of realistic measurements, still might lead to some catastrophic consequences later on. So it's much more difficult and relevant to focus on weak faults than strong faults. So what we were considering weak faults, if I remember correctly, is when the level of faults is at most 20% of the actual measure. So we that are focusing on detecting faults that are in the range 5 to 20% of the real measure. Again, if faults are larger than 50% of the real value or even 100%, you don't really need any complex architecture to detect. It's quite easy. So it's not considered as relevant problem, scientific problem from this perspective. So here, estimation performance of this of different solutions in terms of estimation. So these are the performance of various solutions for the, let's go back, of this estimation layer. So how good are we in having all the measurements from the rest of the sensors for estimating the actual value that has been measured by another sensor? So in this case, we might see that the original proposal was having this kind of perform. Well, as I was saying, this was on the sensor network. We have temperature measurements on 4 sensors. 2 are indoor and 2 are outdoor. And in this case, these are the performance of the first proposal. And you might see how different combinations of models might lead to improving the performance. For instance, usually we've noticed that when we use CNN, convolutional neural network, this was not surprising. Convolutional neural network is in many applications for time series has been showing a very good trade-off in terms of complexity and performance. So not surprisingly, this has been confirmed also for this special case in which convolutional neural networks simply or combined with other techniques. In this case, for instance, we have the convolutional neural network with this LSTM. They usually exhibit good performance for this problem as well. Detection performance, meaning are we able to detect at the classifier that there is a problem without really focusing on where is coming the problem, but just there is a wording. So this is typically measured in terms of residual operating characteristics, meaning plotting the probability of correct detection versus the probability of false alarm. And again, we might see the autoencoder, what we were considering state of the art, was having this kind of performance. In this case, this is performing on this dataset very bad, the original MLP, but we might see how this different based on, yeah, for instance, the CNN should be this one, and is quite good. So as much we go towards this corner, the better we are. So you can easily see in terms of detection performance, which combination shows a very good performance. Then classification or isolation performance. In this case, again, given a fixed probability of false alarm, and given that there is the detection, we are trying now to, are we able to point in the correct sensor or not? So again, the probability of correct classification means that the detection is already in place, but now the decision will be okay. For instance, if the problem is coming from sensor 1, are we assigning the fault to sensor 1 or not? If the detection is in place, but we say that sensor 2 is in fault, while it was sensor 1, this will be a correct detection of the problem, but a wrong isolation. So in this case, with a given false alarm, we are trying to measure how many of the correct classification parts we are performing. And again, we can see that CNN and similar based CNN version are still performing much better than the rest. Accommodation performance is now basically sort of combination, because this performance are just estimation performance in terms how each virtual sensor is capable to predict the measurement. With accommodation performance, here now we are taking into account every time that a sensor's measurement is replaced with the virtual sensor measurement because of a detection performance, what is happening? So basically, this is a kind of combination of the estimation capability of the virtual sensors, but also integrated with the decisions that are coming from the classifier, because you will run the accommodation if there has been a detection and if that sensor has been claimed to be in fault. So this kind of performance takes into account basically all the chain of detection, isolation, and estimation in place. And with this performance, again, we see that the MLP and the autoencoder base were not extremely good, but with this CNN specialty solution, we can have performance that are much more interesting. And finally, of course, the price that we are paying should come somehow. And this is, as expected, again, is coming in terms of complexity. So basically, we were comparing the running time per epoch and the number of the parameters to be training, so trainable parameters. And we might see that in this case, the MLP-based solution that was still sufficiently appealing was much more recent from this perspective, while the other techniques, of course, they are more complex network, and the price that you pay is in terms of complexity and that you need for training and for running the system. And I guess, yeah, that was it.